It's my first non-teaching public talk since January 2020. It's very exciting for me. It's taken me a while to get out, I guess. So today we want to be talking about, give a bit of a brief overview of the research group. I don't know most people here, so won't go on too much about the research team and the projects we're working on, and then move into the sort of the main focus of the case study we're looking at today. So looking at, I guess, better understanding that role for negative emissions technologies in moving towards and achieving net zero, and talking in a bit of detail about about biochar and existing projects we have in this area as an opportunity for the UK for negative emissions technologies. So overall, the research team that I lead at Nottingham, we're a group that's growing quite quickly. We're at the moment, we're about 4 postdocs, recruiting 2 more at the moment, and about 10 PhD students. So it's everything seems to keep growing. And as a result, we end up covering quite a wide range of different application areas and case study areas. At the core of the work that we do is principally focused around life cycle assessment and technoeconomics. And we use these tools to ask questions about emerging technologies and to think about that overall carbon impact, but also thinking about resource aspects, thinking about costs, investment costs, as well as sort of cost effectiveness of different strategies, and really balancing these trade-offs. As one of the earlier speakers was mentioning, there's always trade-offs with these technologies. We can have low carbon options that are using rare materials or come at a higher cost, or other sort of other trade-offs that we need to be considering. And so we generally use these tools where what we're doing is we're evaluating new technologies and really trying to imagine what will happen if we start doing things differently, and mapping that uptake of new technologies to try to meet future carbon budgets and ultimately move towards this net zero target. So we do work in a number of areas. So we work in a number of projects in the transportation space. So we have projects looking at the light duty, so looking at the car fleets in the UK, in the US and China, with our partners at University of Toronto in Canada, and the Chinese Automotive Technology and Research Center in Tianjin. We have other projects with partners at Nottingham and elsewhere, looking at offshore renewables and converting that into low carbon fuels. Looking at new fuel options for marine transport, so ammonia, hydrogen, other sort of alternatives. A bit starting to move into the rail sector as well. Outside of transport, we look a lot at renewable materials, and so working with Mitsubishi UK, which was formerly Lucite, and so trying to understand opportunities for bio-based acrylic materials. But also circular management of acrylics and better retaining that resource within the economy rather than having a single throughput. And we also, my bread and butter back from the day when I was a PhD student was everything about biofuels, and so we do still have quite a lot of interest in renewable fuels, renewable materials as well, and better understanding the sustainability implications of those options. I'm realizing now that since I'm not sat in my home office, I don't see the presenter view and I can't see my notes. So I'm going to do my best to try to explain the next few slides here, guys. I'm also wearing trousers, so this is a good step forward as well. So because if we look at the next couple of slides are coming from the Committee on Climate Change and their report looking towards net zero, and looking at some of the technical options that we have and different scenarios for how we might get close to net zero into the future. And so this here is their core scenario. We can see on the chart moving from 1990 through to 2017 and then onwards to 2050, looking at the core scenario where what we're able to achieve here is a reduction in greenhouse gas emissions by about 75%, 75 to 80%. And that's obviously not getting us to net zero by 2050, but is still involving quite a lot of important interventions. So looking at banning gas boilers in houses in the relative near future, looking at the electrification of the light duty vehicle fleet, and some small amount, the little gray bit below the x-axis there, a very small amount of greenhouse gas removals. But of course, now that we're talking about net zero, we know that this scenario isn't getting us there. We need to do more. We need to do more quickly as well. And so if you look more towards further ambitions and greater changes that we can make, again, if I could see my notes, I could tell you what the differences were with what the assumptions are in this scenario, but you can imagine what it is. We're seeing a lot more decarbonization of those trickier to decarbonize areas, or heavy duty transport, Maybe we're starting to see some synthetic fuels into airplanes, for example. So a lot of potentially higher cost, less certain technologies that we might be able to deploy to try to meet this net zero target. And even under this scenario, we still don't quite get there. We're still left with about 35 million tons of CO2 equivalent per year versus about 800 million tons that we had back in 1990. So still a substantial reduction, getting close to net zero, but we still need to do more. We still need new technologies, new options that businesses can use to decarbonize what they're doing. Also, of course, as other people have been mentioning, thinking about that sort of consumer choice and the behaviors that people have, and what are other options we have to try to address these emissions. And I like this slide because I think it's a good summary of exactly where we work in our research space. So we work a lot with companies, with people developing new technologies to try to understand, what's that viability of what they're trying to do? What role could it play in further reducing these emissions if we're aiming towards net zero? But at the same time, thinking about that trade-off, is it going to make sense? We may have technologies that we could do, that we could use to reduce greenhouse gas emissions, but would it actually be more worthwhile for us to instead do what we do currently and then invest more in negative emissions technologies to compensate for those more difficult to mitigate sectors? And I think this is a really important decision point that a lot of companies find themselves at now. They want to try to get as close to net zero themselves, but at some point the options available to them will become too expensive, and they may need to be thinking about negative emissions technologies, either that they're operating themselves or that they're supporting and getting access to those credits. If we look at the opportunities for negative emissions technologies, this is from, again in my note, the Royal Society, the Royal Academy of Engineering. Excellent. So a report on greenhouse gas removals, on negative emissions technologies, and we can see here different ways we can capture carbon and sequester it and pull it out of the atmosphere. We can see the estimated costs that we're expecting to see for these different options and the potential scale that might be available in the UK. If we were achieving this maximum scale in the UK for all of these options, well, then we could mitigate about 25% of our current emissions. So we could achieve a net zero with that core scenario going forward if we do all of this. But it's immensely expensive, up to 30 billion pounds per year if we're looking at these cost estimates to achieve that much greenhouse gas removals. So a very expensive proposition, and there's going to be some optimal solution that's somewhere in the middle.
BECCS and DACS, please.
Oh, sorry. So BECCS is bioenergy, where we're capturing the CO2 and sinking it in the ground. DACS is our direct air capture, where we're pulling that CO2 directly and capturing with our amines and sinking it in the ground. Apologies. Yeah. So there's a role for greenhouse gas removals, but in my view, it's going to be, we should be thinking about it as being modest. It's always going to be an additional cost, and there are going to be options that we could take to address these emissions in other ways. And ideally, we want to be moving towards near zero, as close to zero as we can get with cost-effective measures, and then thinking about our negative emissions technologies as balancing all those different bits that we couldn't avoid in the first place, because we have practical and we have technical constraints as well as financial constraints to deploying these greenhouse gas removals technologies. And going forward, I think it's still early days, and so we need to identify what are our cost-effective options, what options will we have available to us that will make sense in a UK context as we're moving towards 2050. And so this is where our work on biochar comes in. And so I don't know if people will be familiar with biochar. Just very, very quickly, it's essentially making a coal-like charcoal substance from biomass, where if done correctly, we can create a very stable form of carbon that can then be deposited onto soils, and it can remain there, sequestering that carbon content over a very long term. So thinking of hundreds, thousands and thousands of years potentially. In some contexts, we can also see additional benefits from applying biochar in agriculture and forestry settings. We can help with water retention, providing nutrients, potentially increasing the yield of agricultural products as well. So the mechanism to achieve negative emissions with biochar is we think about starting with our carbon dioxide in the atmosphere and growing our biomass. In this case, let's say it's a tree. So that tree growth is capturing CO2, converting it into carbon that's contained in that biomass material. If we then take that material, produce char from it, we won't have full retention of that carbon, but we will be able to recover some heat and power from that char production process. we'll end up with our carbon-rich product that we can then sequester, essentially that CO2 that originated in the atmosphere, sequester it in that char over very long time scales in land-based applications. Okay, I'm going to run out of time too. I was hoping I'd have some time for questions, but do our best. Challenges for biochar. I think it's the same as the challenges for biofuels, is identifying a sustainable biomass supply. It isn't going to be inherently limited with competing uses for biomass. We see a lot of drives for biomass for our BECCS, for our bioenergy with carbon capture, for low carbon fuels, materials, building materials, etc. And so understanding that role for biochar, what feedstocks will make sense to put into this product to achieve negative emissions, that's a big question that we have, and ensuring that we avoid unintended consequences of using biomass for this application. Our cost of avoided emissions, of course, is an important question. Are we going to be competitive with other negative emissions technologies? To do so, we need a low-cost feedstock. And the other big question mark, well, not necessarily a question mark, but something that needs further proving if we think about posing this problem, is being able to demonstrate the permanence of carbon sequestration, to be able to create that scientific foundation for a business model where we can prove that we can sequester this carbon for long periods of time, so we can create markets to be able to sell this greenhouse gas removal to customers. So at Nottingham, we're the lead partner of quite a large project, which is our biochar demonstrator. It's part of the greenhouse gas removals hub that UKRI has funded recently, looking at a number of greenhouse gas removals technologies. In the biochar demonstrator, we'll be depositing about 200 tons of biochar over the next few years into various field trials, agriculture, forestry, peatland restoration projects as well. And so covering quite a large area of looking at those technical aspects, so the char production, demonstrating permanence, field trials, etc. And the role that we have is trying to understand that overall picture from a greenhouse gas and financial perspective. Again, identifying what are our routes going forward that could potentially make sense in the UK to make use of available feedstocks to produce biochar and to put it into applications where we can see ideally quite a lot of co-benefits to help to make the story a little bit stronger. 1 minute to go through a whole case study. I'm going to do my best. As part of a related project funded through BAYES, a phase 1 project for looking at greenhouse gas removals, we worked with a couple of companies looking at food waste as a feedstock for biochar production. And so here specifically, we're not just looking at food waste as itself, but looking at a digestate that comes out of a food waste anaerobic digestion facility. So if we're managing our food waste by producing biogas in an AD plant, we have digestate, a solid material that hasn't been converted. And this is a great feedstock to think about for biochar because we can't do much else with it. There's plastic contamination in this feedstock, so we can't just apply it to land to make use of the nutrient content. It's also very wet, and so if we wanted to put it into an energy application, the amount of energy we'd spend to dry it would be excessive. We wouldn't get very much net energy out. We have a process at Nottingham that, for the interest of time, I won't get into, but allows us to directly convert this wet feedstock into biochar. That we can then look at as a greenhouse gas removal product. And so in the slides that I'll happily talk about over lunch, but we'll not have much time to show now, we're basically showing the results from this phase 1 project where we're looking at different scenarios for biochar production, a non-commercial demonstration facility, so looking at what we're planning to do for phase 2, and then looking at different future scenarios in 2030. It's a little bit silly to try to go through it all, I think. But all in all, again, taking the full life cycle perspective where we're starting with our digestate from AD, we're moving this through to our production process to produce our biochar, spreading it on the field and looking at that net carbon sequestration in our biochar product. From a greenhouse gas perspective, so this is looking at our 5 different scenarios in our phase 2, proposed phase 2 situation, which is not ideal. We have very large transport distances between the AD facility and the biochar facility. We are still able to achieve substantially negative emissions, so net sequestration of atmospheric CO2. But when we move into our expected commercial performance, then this is where we're really starting to see significant net reductions. The big black bar is that carbon that's sunk in our biochar, where we've pulled out of the atmosphere. These other shaded regions are looking at other co-benefits, so looking at fertilization, looking at avoided emissions from agriculture. And above the x-axis, we see those energy inputs for transport and for running our processes, but significantly negative emissions overall. So it's exactly what we wanted to see. And from a cost standpoint, not bad either. Phase 2, it's not commercial, doesn't matter. It's very expensive. Nobody should ever pay that much money for a greenhouse negative emission technology, I don't think. But once again, when we think about the more optimized production, we can achieve a cost of avoided greenhouse gas emissions, of negative greenhouse gas emissions, of less than 100 pounds per ton of CO2, which puts us in a very competitive place with other negative emissions technologies. Challenge here is the scale of deployment. There's not that much food waste in the UK, and hopefully in the future there'll be even less, because that would be much better for the planet and the environment to minimize that availability of food waste for us. There will always be unavoidable food waste. If we use all of that, converted it into biochar after an anaerobic digestion process, we could be pulling about 180,000 tons of CO2 per year out of the atmosphere. In the grand scheme of things, a small drop in the bucket. But a low-hanging fruit in terms of a feedstock that's available for biochar production. Going forward, as part of these projects, looking at increasing that feedstock supply, looking at different sources, and what does that mean again for that net greenhouse gas balance, but also for the financial viability of biochar. Again, apologies for overrunning, but I've done my best. You know, the odds all we can ask. But again, just quick before I go, acknowledgements to the co-authors. So Colin Snaith, who leads the demonstrator project, Will Meredith, Sarah Rogers, who did all the case study work, and Disney, who's picking that up as the postdoc on the project, and our industry partners, Severn Trent Green Power and CPL. Thank you very much.
For you to share this information with you. Okay, thank you.